Today we're going to continue on with our discussions of circles and different angles that can show up in circles. We're still kind of pretty basic on our discussion at this point. It will continue to get a little bit more complicated, but today is not a whole lot worse than it was yesterday, just a new set of definitions and a new rule that goes along with them. Okay, first thing we've got is a new definition. Okay, today we're going to be looking at what are called inscribed angles. Okay, well, an inscribed angle is an angle in a circle. And what's different about an inscribed angle today as opposed to a central angle yesterday? Central angles had their vertex on the center of the circle. Inscribed angles are going to have their vertex on the circle itself. Okay, so an inscribed angle is an angle in a circle that has its vertex on the circle, and its endpoints are going to be on the circle as well. Okay, so if you'd like a basic diagram to go along with that definition, then here is a possibility. And if you would like a statement describing that particular situation, well, there you go. Angle ABC is an inscribed angle of circle D. And just like with yesterday, I want to emphasize that, yes, we are needing to use the three-point naming system on our angles because it is very possible that there will be more than one angle at vertex B. So if we just called it angle B, then that could very quickly become confusing. Okay, and also keep in mind that we still name our circles according to what their center point is. Okay, so we call that guy circle D. Okay. Now this wording is just the same as it was yesterday, so you probably don't need to worry about copying that down. But just like with central angles, an inscribed angle intersects a circle at 2 points or 2 places. And again, those 2 points are the endpoint of an arc that is on the circle. And of course, we can categorize our arcs as minor if they are smaller than half the circle, or major if they are more than half the circle, or a semicircle if it's exactly half the circle, and so on. So we're still going to have a good bit of discussion going on about arcs that are caught in these angles, what we call the intercepted arcs. Okay. Now, just like yesterday, there is a connection between what an inscribed angle is doing and what its intercepted arc is doing. Okay, and that connection, this one requires a little bit more thought, but it's actually not that bad, and it's kind of common sense. The measure of the inscribed angle is going to equal half the measure of the intercepted arc. And if you wanted to turn that English around backwards and think about it the other direction, that also says that the arc is twice as big as the angle. Okay, so 2 ways to think about it. Either the angle is half as big as the arc, or the arc is twice as big as the angle. Okay. And there's a diagram that goes along with that if you would like one. And as I said, there's a little bit of common sense. If you think about where the vertex of an inscribed angle is positioned, okay, it's positioned way out here on the circumference of the circle. Yesterday, when we were talking about central angles, it was positioned on the center point of the circle. So kind of a different way of thinking about it is the vertex has gotten twice as far away from its endpoints as it was before. Okay, it's gotten twice as far away. In the process of getting twice as far away, the angle actually has to shorten up its measurement because its endpoints are still grabbing the circle at the same position. So when that vertex pulls further back, okay, the legs get longer, but the angle has to collapse a little bit. So we get an angle measurement that is smaller than we got yesterday. Yesterday, the angle measurement was exactly the same as the intercepted arc. Today, it's only going to be half as big as the intercepted arc. Okay, and once again, just like yesterday, we are still dealing with our arc measurements in degrees. Okay, we will look at some other ways of considering those measurements later on, but for right now, we're measuring in degrees. Okay, now as we go further into this chapter, you're going to notice that we're going to get more and more rules. There are some special situations that we need to look at with inscribed angles. Okay, so we're going to take a little time, particularly I believe there's 3 of them that we're going to look at. And I think what you're going to find is that a lot of them are common sense anyway. But we do still take time out of our normal geometry day to talk about the common sense stuff also. Okay, so let's have a look. Okay. All 3 of these things we're going to look at are theorems. And remember the difference between a postulate and a theorem. Postulates are that common sense stuff. Okay, and theorems are the things that require drawn out explanation, okay, in order to understand, okay, or to be proven to be true. Okay, so these are theorems. These are things that they've taken the time to explain in great detail. Somebody has written it out step at a time. Okay, but the first theorem says if 2 inscribed angles were to have endpoints defining the same arc, then the angles are congruent. Okay, that definition, that's not really really very clear the way that's worded, but that's about as easy as I could make it. But here's a diagram that could possibly help you understand exactly what it's talking about. Okay, here you can see in the diagram we have 2 inscribed angles, one that I've colored in red and one that I've colored in blue. And it fits the description of the theorem because the theorem says that they have endpoints defining the same arc. Okay, they have the same intercepted arc. So the red inscribed angle reaches out and grabs a hold of the circle, and then the blue inscribed angle reaches out and grabs a hold of the exact same locations as the red inscribed angle did. So they define the same arc, or they have the same intercepted arc. The theorem says when this happens, those 2 angles are going to be congruent. Okay, so by the theorem, the red angle and the blue angle are congruent. I didn't label them for us to name them or anything because the figure's already cluttered enough as it is. Okay, but this is very much common sense, and let me show you why I'm going to say it's common sense. Okay. Let's say that we have an angle measurement inside of here. I'm going to give this angle measurement, that red one, I'm going to give it a measurement of x. Okay, give it a measurement of x. Then if I were to ask you what is going on with the measurement of its intercepted arc. Okay, well, what's the rule between an inscribed angle and its intercepted arc? Okay, well, the rule is that you can read it 2 different ways. You can either say that the angle is going to be half as big as the arc, or the arc is going to be twice as big as the angle. Okay, so if I said the angle is x and the arc has to be twice that big, then what would the arc be? 2x, right? That would go along with the rule that the arc is going to be twice as big as the angle. Okay, all right, and that was all talking about the red angle. Now let's look at the blue one. Doesn't the blue one have this same intercepted arc? Yeah. Okay, so the same rule still is going to apply. An intercepted or an inscribed angle is either going to be half as big as its arc, or the arc is going to be twice as big as the angle. So if this arc is 2x, then what do you know about this blue inscribed angle? It's got to be half that big, which is going to be x. That's all this theorem says, that if 2 angles have 2 inscribed angles have endpoints at the same location, then the angles are going to be the exact same measurement. I would actually make the argument that we probably could have figured that out on our own in a problem, and we wouldn't have needed a theorem. But the theorem does exist, so there you go. Okay, you can follow that along. Okay, but there's the first theorem. Now another theorem. This one's a little bit more useful, happens a little more often in circles. And it says an inscribed angle is a right angle if its endpoints are on a diameter. Well, here's a diagram to go along with that. And I'm going to walk you through this one as well because I'm going to make the argument once again that this is very much common sense. Okay, so let's assume for a moment that we do not know that the blue angle is a right angle. We don't have this theorem telling us it's true. But we do know that this red line segment coming across the circle is a diameter. How do we know it's a diameter? Well, it passes through the center point of the circle. Okay, so we have a diameter, and we have this blue angle which is reaching out and it's grabbing a hold of the ends of the diameter. The theorem says that that makes the angle a right angle. I'm going to say that, you know what, we don't need the theorem to tell us that. If I asked you, what is the measurement of this arc? What would you say? 180 degrees, right? Because if it's grabbing a hold of the endpoints of the diameter, well, that diameter cuts your circle into a semicircle. Okay, that's halfway around the circle. That would force this arc to be 180 degrees. It doesn't have any choice. Okay, and as we've discovered today, what is the relationship between an arc and the inscribed angle? The arc is twice as big as the angle, or the angle is half as big as the arc. So if the angle is half as big, then what's that going to make this angle measure? 90 degrees. It doesn't have any choice, and we really didn't need that theorem to come along and tell us that, but it is one of the theorems, okay, that shows up in most textbooks. So there it is. Okay, but again, it kind of common sense. Okay. All right, one more theorem. This one is not quite as obvious, but there's still a good bit of common sense to it. Okay, and this theorem says a quadrilateral can be inscribed in a circle if its opposite angles are supplementary. And if you're not familiar with the word inscribed, okay, it's probably something we haven't spent much time teaching you about in previous years, and we haven't discussed it this year. Okay, but you will see it on things like the PSAT or the plan, stuff like that. Inscribed means it fits perfectly inside. Okay, and that means that all of the vertices are making contact with something that's larger. Okay, you got one shape inside of another, and they fit perfectly inside of each other. And here's an example of what that is saying. You have a quadrilateral that is inside of a circle, inscribed in the circle, and all of the vertices of the quadrilateral are making contact with the circumference of the circle. That is inscribed. Now what the theorem is saying is its opposite angles are going to be supplementary. That's how come I numbered these angles inside of this diagram, so we kind of can refer to what's opposite. Okay, so it's very clear to see in the diagram that angle 1 and angle 3 are opposite angles. Angle 4 and angle 2 are opposite angles. The theorem establishes for us that if you take angle 1 and angle 3 and add them up, you get 180 degrees. And if you take angle 2 and angle 4 and add them up, then you also get 180 degrees. Now, once again, I'm going to claim that this is kind of common sense. And let me show you why I think it's common sense on the picture. Okay, this first row right here says angle 1 plus angle 3 equals 180 degrees. That's not a very obvious thing when you just look at it, but let's look at what it's actually saying. Angle 1, which is here, there, and there, makes contact here, makes contact there, and it has its arc going all the way around there, right? Okay, now let's also look at angle 3, which is here. Makes contact in the same locations, and its arc is over here. Aside from my board doing some weird things. Okay, when you look at the green and the red that I just colored in going around, did I fill in the entire circle? It did fill in the entire circle. Those two arcs, when combined, created an entire circle. And what do we know about entire circles? How much does it measure to go all the way around? It goes 360 degrees all the way around the circle. Okay, now those are the arcs. Now what's the relationship between inscribed angles like this red one and like this green one? What's their relationship with their arcs? The angles are half as big as the arcs are. Okay, so if together they are 360 degrees, and the angles are going to be half that big, then what are the angles? 180 degrees, which is exactly what the formula or the theorem establishes. And you can find that on this as well, on angle 2 and angle 4. If you did the exact same thing, you would find out that those inscribed angles, their arcs build an entire circle as well. So again, a little bit of common sense on the theorems, okay, but it doesn't mean that it's not worth our time to take a look at them, okay, but there's that. All right, enough of the theorems and the rules and all that kind of stuff. Let's take a look at an example and see if we can figure out some questions that are going to follow. Okay, so we've got a circle here and we've got a bunch of questions that are going to follow. And before we get to the questions, I want to make an important point. Didn't really say much about it yesterday on our discussion of central angles because our central angles were pretty much identifying the center of the circle for us. Do not make the assumption that you have a diameter unless you are certain that the thing you're calling a diameter does actually pass through the center of the circle. Okay, so for example, I've got point A in there. Okay, the proper assumption would be that point A is the center of the circle. That means that line segment CE coming across here is not a diameter. We wouldn't want to treat it like a diameter because that would give it some different properties and could cause us to miss some problems. Okay, but let's start off with some baby steps. Name an inscribed angle. Okay, so just pick one out. Anybody name an inscribed angle out of this diagram? Angle DBC? Absolutely, that is an inscribed angle. Its vertex is on the circle itself, and its endpoints reach out also to the circle. What others? CED, yes, angle CED is one of them. Any others? DBC, we've got this one right there. CED, we've got this one right there. BDE, absolutely, angle BDE gives us that right there. Is there another? Yeah, we got to get this one down here at vertex C. So you can say BCE. Okay, so you got to really keep your eyes open with inscribed angles because sometimes they can kind of disguise themselves. Your eyes get playing tricks on you a little bit. So just kind of pay attention to what you're doing there. All right. Now let's answer a question here. Next question asks us for the measure of angle DEC. Okay, you may want to mark it, get in the habit of marking it in your picture, especially if you're not real good at staying focused on where you're thinking in a diagram. DEC is here, okay, that angle. Okay. Anybody come up with a strategy that we might be able to use to figure out what's going on with angle DEC? One of the things to notice on this one, this goes hand in hand with one of the theorems that we just saw a few moments ago. Notice that angle DEC has endpoints here and here. Is that the only inscribed angle that has endpoints at that location? No, we have another angle that also terminates at the same place as angle DEC does. And there's a theorem that deals with that. Remember, what did it say? If you have two angles that use the same terminate at the same place, then it's the exact same measurement. So if we can figure out what is going on with this arc, well, it's the same arc for both of those angles. Okay, well, what can we do to figure out what's going on with this arc? Okay, well, we've got this angle measurement back there is going to play some kind of a role. Well, what's the connection? We have an inscribed angle and we have an arc. What's the relationship between the two? They're not congruent because it's not a central angle, but the angle will be half as big as the arc, or the arc will be twice as big as the angle. So if the angle is 80 and the arc's going to be twice that big, then what do you know about this arc? Oh, sorry. I was thinking one thing and wrote something totally different. Okay, 160 degrees. Okay, so that arc is 160 degrees. That's good to know. We may need that for another problem later on. Okay, but what does that mean about this angle that we're trying to work on right now? Angle DEC. What do you know about that? Okay, yes, it's exactly half of its arc. So if the arc is 160, the angle must be half that much. The measure of angle DEC is 80 degrees. And if you were clever enough to catch that you had that one theorem that says if you have two angles that start off that use the same, or two inscribed angles that use the same inscribed or included angle or included arc, pardon me, that their measurements will be the same, 80 degrees and 80 degrees right there. Okay. Our next question asks for the measure of arc dB. Measure of arc dB. Okay, I'm going to erase some of this clutter. Where's dB at? There. Okay. All right. What's preventing us from being able to answer the measure of arc dB? Do we have all the information we need, or is there something missing? Okay. How about this guy right there? Okay, we have part of arc dB. Okay, we've got EB, but we don't have D to E. Okay, so what can you think of? What might we be able to do to figure out what measurement is missing there on arc DE? Exactly. Good thing to notice would be that we have almost the entire circle. The only thing that is missing from the entire circle going around the circumference is arc DE right there. Okay, so if that's the case, then all we have to do is figure out how many degrees from 360 is missing. So we could say 55 that we know, 85 that we know, 160 that we know, and the arc ED that we do not know. They're supposed to add up to be 360 degrees. Well, let's just see what's missing. 55 and 85 is 140, plus another 160 is 300. I think most people right there can spot that it's going to be a 60. Subtract 300 from both sides. X is 60. That is the information that's missing right there. Okay. So now, based on this new information, can you now tell me what the measurement of arc dB is? Exactly. You add 60 and 55, and that's it, 115. Somebody got it. Okay. Again, I'm going to erase some of my clutter. Okay, a lot of stuff going on in this circle. One more question. The measure of angle EDB is what? I have no idea. Let's find it in the picture. EDB is here, this little guy. Okay. And you see anything else in the picture that can be used to help us with the measure of angle EDB? We've got its arc, don't we? We have its arc out here. It reaches out, it connects there and there. Here's its arc, and we have that measurement. Okay, so what's the connection between that arc EB and the measure of angle EDB? What's the relationship there? It's going to be half. The angle is going to be half as big as the arc, so we have a 55-degree arc, and we will need to know what is half that big, because that's what the angle is going to do. And in this case, what do we end up with there? It's like 27.5 degrees, I believe, unless I've made some kind of mistake there. Okay, I believe it's 27.5 degrees. Is it possible that we'll end up with angle measurements that are not whole number degrees? Sure, they're just numbers, decimal numbers, fractions. It's all good. Okay, as long as you've done your work right, you should be able to get to the right answers. Okay. All right, there is a worksheet that goes along with this assignment, and that's it.